Nuclear chemistry. So maybe many of you are familiar of this because of the everyday applications that it has. I don't even know if it's a good application, but every time when you hear about nuclear thing, what's the country associated with nuclear thing? That's also start with letter N. Okay, so we're talking about North Korea. Okay, their leader there, Donald Trump Kim. Okay, always love to test his nuclear missile, right? So remember, Donald Trump and Kanye are BFF. So Kanye has his Kim, so Donald Trump has also his own Kim. So I think that's what makes them BFF. Okay, because Donald Trump say when she was president, he fell in love with the North Korean leader Kim, whatever the last two names is. Okay, now if you're going to look about nuclear chemistry, everything has something to do that is happening in what we call the nucleus. Okay, so everything, if we're going to what we could look at what we have discussed so far from chapter 1 to chapter 19, everything has something to do with the electrons. Okay, now the study of the reactions involving energies in atomic nuclei, that's your nuclear chemistry. So everything that happen within the nucleus. So what do you find in the nucleus? You have there, okay, your proton and the neutron. But all reactions that we have, if you're going to look at this, it's just what? Involving electron. So for the 19 chapters that we have, we might have what we call discuss something about this, what we call proton, nucleon, or other parts of the atom. Okay, but in terms of the reactions that we have, okay, all reactions are involving electrons. So what we're going to discuss, at least for this 1 hour lecture, is what happened in the nucleus. So the study of the chemical reactions in atomic nuclei, it began when Antoine Becquerel discovered the natural radioactivity. And its growth can be credited to the Curies. Okay? Uh, especially Marie Curie. Okay? The one who got 2 Nobel Prize in both chemistry and physics. So all nuclei would contain fundamental particles. The only one that you don't, what we call all nuclei that contains electron, they have this what we call the fundamental particles. The exception that they have is H2, because H2 has what? A proton and the nuclei. And some of the nuclei are what we call unstable. So if you're going to have a review, okay, you're familiar with the term atomic number. So this is the number of protons in the nucleus. And atomic number always belong to what? One particular element. Okay? And you're also familiar with what we call the mass number. So the mass number is just the number of particles in the nucleus, the number of protons and the number of the neutrons. So whenever you write an equation, okay, so this is your atomic number and this is your mass number. Okay, and the X there, that's your element symbol. Now, if we're going to look at the sum of atomic particles that we have, and I think this is the one that you should know, okay, when we have a proton, we can put it like this. So when we have a proton, we have what? One atomic number, which is the number of proton, and one mass number, because it doesn't have neutron. And that is synonymous to the element hydrogen. Hydrogen 1. Okay? And then you have a neutron, wherein it has zero atomic number and 1 mass number, because you only have 1 neutron there. So that's 1 atomic particle, another atomic particle. And then you have an electron. Okay? So an electron can be described as a -1 because of the sign, and 0 mass number because you don't have no protons and neutrons there. And sometimes you call it a beta particle. Okay? So in terms of atomic number, it's 0, and mass number is -1. And then you have a positron. So what do you think is the root word of positron? Okay? So positron is just the positive electron. So instead of a negative number there, or a negative atomic number, you will have a positive one, what we call the atomic number. And last but not the least is the alpha particle, which has 2 as the atomic number and mass number equals to 4, or it's just the element helium. So these are some of the so-called subatomic particles that you have. Okay? Now you also have this so-called balancing. So this is already what? The third type of balancing that you have. First, the balancing simple equation for simple reaction, and then balancing redox reaction from last week class. And then we have now balancing nuclear equation. So when you balance nuclear equation, you just try to make sure that the sum of the protons plus neutrons in the products must equals to the sum of protons plus neutrons in the reactants. Okay? But there's a difference here between what we have discussed or what you have learned before. You don't have to have the same elements. Okay? The one that you want to know is the mass number on both sides must be the same. The total number of neutrons is equals to on both sides. The total number of protons is equal on both sides. So if you have here uranium-235 reacting with a neutron, you produce cesium-55 and rubidium-37 with 2 neutrons. So if you're going to look at this, so you have here what? 235 plus 1, so that's 236. And then on this side, 138, 96 times 2 plus 1, that is also 236. And then you can also have this conservation of atomic number or nuclear charge. And again, okay, it's just making sure that the atomic charge on both sides are equal. It doesn't necessarily mean you have the same type of element. So we're going to use the same thing here. So you have 92 plus 0. So that's 92. And then you have here 55, 37, and 0. And then you have here 55, 37 plus 0. So that is also 92. So that's the only thing that I would say you can focus your attention in this chapter for questions that's being asked in your exam. So let's try to work with some with the reaction here. So polonium-212 decays by alpha emission. So write the balanced nuclear equation of the decay of polonium-212. So all you need to do is you need the periodic table. So you write 212 there, polonium, and then find the atomic number of your polonium. So you can only do it if you have the periodic table. So that would be equals to what? Anyone? What does polonium-212 equals to? So if you have the periodic table, that is equals to 84. So it says here decays by alpha emission. So that means one of the product is an alpha particle. So just put it like this. So one of the what we call product is this one. So you have to find what is the one that is missing. So how do we do that? So you have there 84 and you have here 2. So this must be 82. And then you look at the periodic table. What is the element that has an atomic number equals to 82? Anyone?
Lead.
Okay. So lead. And then you have here 4. And then you have here what? 4 or 212 minus 4. So that's the one that you have. So this is the element that you have. Now to double check, you add both sides, both what we call species here. So the number of their atomic number and mass number should be the same on both sides. Okay, you can also write this as this one, because alpha particle is also helium. Okay, so that's the thing that you need to, we could say, concentrate. Now, in terms of what we could comparing the chemical reaction that you know with the nuclear reaction, so this is the table that lists down the difference. So as you know it, there's only rearrangement of atoms caused by the breaking and formation of bond. So what does it mean? Whatever's the starting element, okay, it's still there in the product. Like nitrogen plus hydrogen to produce ammonia. So everything is preserved. But in the nuclear reaction, as you could see, they can be converted from one element to another. Okay? So that's one of the main difference that we have here. You can create another element in a nuclear reaction. And then in a chemical reaction, only electrons is the one that participate in the reaction. But here, you have the protons, the neutrons, the electrons, and other elementary particles that we have just discussed can be involved. And then here, reactions are accompanied by absorption or release of relatively small amount of energy. But if you go with the nuclear reaction, they're accompanied by the absorption or release of tremendous amount of energy. That's the basis of your nuclear energy. And that is also the basis of your nuclear arms. That's one of the biggest regret by Albert Einstein. Okay? Because he's the one who proposed that you can tap the nucleus as source of energy. Okay? And if you're going to look at these rates of reaction are influenced by temperature, pressure, concentration, and catalyst, and these are not affected if you have a nuclear reaction. So there's really a big difference between the two reactions. Okay? So what I'm going to do here in the next slides is just a series of the common reaction or a common nuclear reaction. So if you have this beta decay, it's usually a decrease. Okay? In the number of neutrons by 1. So if you have a beta decay, so you have a decrease in the number of neutrons. So you expect here the beta particle to be one of the product. Okay? Decrease in number of neutrons by 1, increase in the number of protons by 1. So your carbon 6 will form, and your carbon 14 will form N14 and a beta particle. Your K40 will form calcium 40 and beta particle. So if you're going to look at the reaction here of a beta decay, so you have here a neutron that will break down to give you a proton and an electron. Positron, on the other hand, it's similar to the beta decay, okay? But the only difference is what? Instead of the neutron that is breaking down, you have a proton breaking down to form a neutron and a positron. So you have their C11 to form B11 and a positron. You have K38 forming argon and a positron. So there's an increase in the number of neutrons and there's a decrease in the number of protons. And then you have the electron capture. So from the word itself, your electron should be in the reactant side. So what do you expect? There would always be a increase in the number of neutrons by 1. So you have here what? 18, and you have here 17. And you have here 26, and you have here 25. And if you're going to look at the overall reaction here, you have a proton that reacts with an electron to give you a neutron. Okay? And then alpha decay, the example that we have. So one corresponding features of this is you form an alpha particle, which is helium. Okay? And then you have also this so-called spontaneous fission. So you have here the formation of 2 neutrons. Okay? Which what we call the special case thing. So if we're going to look at the table or the periodic table, we can find some elements that are what we call radioactive. And some elements they found to be what we call stable. So if you're going to get the neutron to proton ratio, like this one, above that what we call the number, they have this so-called belt of stability. Okay, so if this is the number of protons, this is the number of neutrons. So if it's a 1:1 mole ratio, what we call 1:1 ratio, like if you have a C12, you have 6 proton and 6 neutrons. So when they plot the belt of stability here, so they found out that this is the region where most of the elements are what we call stable. And they found out that if the nitrogen neutron to proton ratio is too large, beta decay is the one that is favored. And if the neutron to proton ratio is too small, positron decay or electron capture is the one that is what we call commonly observed. So if you're going to look at these stable nuclei that are in the belt of stability, this is where most the radioactive nuclei lie. So the radioactive nuclei, most of the radioactive nuclei would lie outside this belt. Above the belt, as I've told you, beta decay is the one that is preferred. Below the belt, the positron decay or the electron capture is the one that is what we call observed. And out of this observation, they were able to come up some statement with regards to nuclear stability. So they found out that certain numbers of neutrons and protons are extra stable, especially like this one. The one that has 2, 8, 20, 50, 82, and 126. Okay? There are what we call extra stable numbers of electrons in what? The noble gases. And nucleon number with even numbers of both protons and neutrons are more stable than those with odd numbers of neutrons and protons. What can you say about it? Even the word, right? Even versus odd. So the odd numbers, they have what we call some odd properties. Okay? And all isotopes of the elements with atomic numbers higher than 83 are radioactive. And all isotopes of technetium and promethium are radioactive. So those are the stuff that they, what we could look. So as an example, why even numbers has more stable than odd numbers. So you have, let's say, 1050. So in 1050, you have 10 stable isotope versus 1051. So they're both tin element. The only one that makes it deeper is the nuclei that they have. So they only have what? 2 stable isotopes. So if you're going to look at the number of stable isotopes with even and odd numbers of proton and neutrons, so if it's both odd number of protons and neutrons, there are only 4 stable isotopes. If one is odd and the other one is even, there's 50. If proton is even and neutrons is odd number, there's 53. But if both protons and neutrons are even, there's 164. Okay, stable isotopes. Now, let's look at this, what we call nuclear binding energy. And this is Albert Einstein's greatest contribution. What is Albert Einstein known for? Anyone?
The equation of the speed of light.
The what?
A equals mc squared.
So he's known for this one, right? But
Yeah.
did you know that he got the Nobel Prize not because of this? What is he credited for in his Nobel Prize? Anyone?
Photons?
The photoelectric effect.
Okay. So Albert Einstein is credited for the Nobel Prize for the photoelectric effect, which he got in what? 1905. But he's more remembered for this theory of relativity. Okay. So he says here, energy is just equals to mass times the speed of light. Now you ask yourself, where are you going to get this mass? Or what does this mass really mean? Because if you're going to look at it, it's really like this, right? But the mass that you have there, that's what you call the mass defect. So I think maybe this is the first explanation on how you understand this, what we call E equals to mc squared. Okay. Now, what is delta M equals to? So delta M, or the so-called mass defect, that is just the difference if you're going to separate the subatomic particle within an atom and subtract it with the mass of the atom. So you got this? You get the number of proton and multiply it with its mass, and then add it with the number of neutron and multiply it with the mass, and then subtract it with the overall atomic mass of that given atom. And voila, you will see a difference there, as seen here. So if this is the proton mass and this is the neutron mass, this is the number of neutron and this is the number of proton, you subtract it with the overall atomic mass, you will get this value, right? So there is what we call a mass defect. Now he stated that that mass defect is enough to be a source of energy. Okay? Why? So if you're going to use that number here, you multiply it with the squared of the speed of light, how much do you get? This amount. So is this big or small? So if we're going to convert this one, 1 kilogram is equals to 6.022 times 10 to the 26 atomic mass unit. Okay, and 1 joule is equals to kilogram per meter squared per second squared. That is equivalent to this one. It's so small, right? But that's just what? That's just the energy from one atom. How many atoms do we have in 1 mole of a substance? We have this one. So if you're going to multiply it, this is the amount of energy that you have. Look at the number. We don't have that number in our calculations in Gen Chem 2. Usually it's what? 10 to the 5 or 10 to the 6. But this is the amount of energy that is produced in 1 mole of fluorine. Okay, so that's the basis of your nuclear reaction. That's the basis of our nuclear energy or nuclear, what we call bomb. So if you're going to look at the nuclear binding energy, this is the amount of energy that can be generated. And if you're going to look at this in terms of nucleons, so this is the amount of energy that you can have. Okay? So that's the basis of this nuclear thing that we have. And if we're going to look at the nuclear binding energy for nucleon versus mass number, this is how it looks like. And the most common that they have is that one. So they said here, the higher, okay, the ratio of nuclear binding energy over the nucleon, the higher is the nuclear stability. So this graph here allows us to compare the stability of all nuclei on a common basis. Okay, so you see a steep rise here on this side. So the highest binding energy nucleon belong to element with intermediate mass. The one that is around what, 40? And the greatest is for what, Fe? I think that's the highest that you have there. So it means that the net attractive forces among the particles that you have here are much better. Now, if we have the basis of this, what we call the nuclear bomb, or the E equals to mc squared, nuclear reaction has something to do also with decay. And the kinetics that it follows is usually what? First order. So this might be, this could be another source of the question that will come out in your exam. Okay? So what do you know about the first order reaction? So I just let them run. I don't know what's happening in our neighborhood. As long as our building is not on fire, then we'll be fine. So this element that you have there, when they undergo nuclear reaction, they usually produce other elements, okay, like the daughter that they have here. So the rate that they have here is just equals to, rate is equals to alpha of n. And since they follow the first order reaction, this is what we have. I hope you still remember that thing. You still remember that, like this? If I'm not mistaken, it's You still remember that thing?
Yeah.
So isn't it the same as that? So you just apply the first order reaction in is what we call decay. And the alpha here, that's your decay constant. In our thing, the K there, that is your rate constant. So if you're looking for the half-life, this is what you have. In our first order, it's like this. So it's just the same as what we have discussed in chapter 13. Now, just to give you an idea about the half-life of these what we call materials that we have. So uranium-238 upon alpha particle or alpha decay, it produced something that would last for times 10 to the 9 years. Okay, but when it is converted to thorium-234, okay, it's going to have a beta decay that lasts for 24.1 day. Your palladium-234 will undergo beta decay. It will last for 1.17 minutes. So some would last years, the other would last in what we call at a much shorter time. And later on, you will see, what does this mean? Okay. So here, I'm just showing you the sequence of decay for uranium 238. So there's a lot of the reaction. And usually, this radioactive decay that they have their uses. Okay? I'm not sure if you're familiar with radiocarbon dating. So in the radiocarbon dating, what they do is they just look at nitrogen-14 reacting with neutron to produce C14, but usually they look at the C14. Okay? The so-called carbon dating. Is this the first time for you to hear this?
No.
Where do you use carbon dating? Like this one. Anyone?
On fossils?
Where do you use carbon dating? Carbon dating is used to determine the age of some biological material. Okay? Industry-wide, the way that they use it, what do you think? They use it to test the vintage wine, right? So they want to see if the wine is really vintage or old. Okay? Carbon dating was also used to what we call, I'm not sure if you're a religious person, but they have this so-called Shroud of Turin. Anyone know what it means? Okay. So they said the Shroud of Turin, Christians believe that's the clothing worn by Jesus Christ when he was buried. And when they tried to do a carbon dating in 1988 in uh, what we called Oxford, University of Zurich, and Arizona, they found the clothing to be around 1260 to 1390 old. Or I mean, the cloth was made around this era. But in 2013, University of Padua, that's in Italy, so it's now in Turin, Italy. So they found out that the age of the cloth is around 3000 to 480. 3000 BC to 400 AD. So they still don't know which is the correct what we call age for that material. Okay, but if you heard the news about material that they discovered to be this old or this was available since this time, the main way that they were able to kept the age of that is using carbon dating. Okay. Why? Because the half-life of C14 is around 5,730. If you want older material like rocks, they use uranium-238 dating. Okay, because the half-life would be what? 4.51 times 9 times 10 to the 9 years. So when you say half-life, if you have 1 gram, after your first half-life, that will be only what? 0.5 gram. So that's one of the, we could say, application of radiocarbon dating. And then you also have this so-called nuclear transmutation. So what do you think is this one? What can you see when we say nuclear transmutation? Okay. What do you mean by mutation? So you could see your element is transformed to another element. And by this nuclear transmutation, this is how they were able to determine the so-called transuranium elements. Okay? Okay, so if you're going to look at atomic number 93 to 111, all of them were prepared in the lab. And all of them were prepared using nuclear transmutation. So they don't exist naturally. They only exist, okay, in the laboratory. So that's what nuclear transmutation is. Now, if you're going to look at the applications that they have, the basis that you have here is nuclear fission. So you have uranium-235 that is going to be split up. Okay. So uranium-235, you have there a proton or a neutron that you react it, and then it's going to break down to give you strontium-90 and xenon-140 and 3 neutron with vast amount of energy. So if you're going to look at the energy that is produced using the theory of relativity, this is the amount of energy. And that's always the source of almost all your nuclear power plants. Okay? We're going to discuss about nuclear plant before. So if you're going to look at how they're efficient compared to this so-called 1 ton of coal. So if you burn 1 ton of coal, this is only the amount of energy that is being produced. Okay. So if you're going to look at the representative fission reaction that they have, okay, so this is the main reaction, and this is the relative amount of the fission products. If you're going to look at the different mass number. You can also have this nuclear chain reaction. So this is a self-sustaining sequence of nuclear fission reaction. So the minimum mass of fissionable material required to generate a self-sustaining nuclear chain reaction is so-called critical mass. So you need to meet the critical mass for the reaction to take place. Okay. But if you're going to look at the nuclear binding thing, that the one that they usually have, so this is the reactant, and these are the what we call products that you can still further utilize, okay, as fuel. You can still break it down. And if you're going to look at the schematic of the atomic bomb, so this is what they have. There's a subcritical uranium-235 there. Then they have a subcritical uranium-235 there, and then they're just going to include it with explosive. In a nuclear reactor, the way that they have it, so they usually have a steam here, they have a shield here, okay? So there's a uranium fuel that they have there. I don't know if you watched the HBO series Chernobyl. I think it's a factual depiction of what happened in Chernobyl, Russia, during, I think, I don't know if you still exist by that time, 1986, when Chernobyl has a meltdown, and it affected the whole Europe. Even when I was growing up during that time, some product, what we called, was affected, because I remember I drink a milk that's imported from Europe. I don't know if you're familiar with the milk birch tree. Birch tree, it's everybody's milk. Okay, I remember when I was a kid. So they have to impound some of the materials that came from what we call that area during that time. And they found out that it's only, I think, rubber that caused that explosion. Okay. Now, the thing with this uranium, it's a very good, what we call the efficient source that you have. So the natural uranium is this one, uranium-238, but you only have a very few of this, what we call uranium-235. So the nuclear, if you have fission, you also have what we call fusion. So the fusion that you have, small molecules reacting to become heavy molecules, like this one, deuterium producing tritium. And the amount of energy that it releases is also high. And if you're going to look at the other reaction, okay, so it's just small molecules or small atoms reacting to produce big atom, and the amount of energy that is what we call being released. And the one that they use is the tokamak magnetic plasma confinement. So this is an approach that's used to generate fusion power using magnetic fields to confine the hot fusion fuel in the form of plasma produced controlled thermonuclear fusion power. So this is a device that uses magnetic field to confine a plasma in the shape of a torus. Okay, but I think for some of you who will become doctors in medicine, there are a lot of radioactive isotopes that is applicable. In fact, they use it. Okay, if you want to image your brain, if ever there's something in your brain, you use the fluorine-18. You can use it also to scan the bone. If you want to monitor the blood circulation, okay, you can use the sodium-24. If you want to find something of tumors in your ocular, brain, or skin tumors, you can use phosphorus-32. If you want to use myocardial scan, you can use potassium-43. If you want to study the calcium metabolism, you can use calcium-47. And if you want to determine the red blood cell volume, spleen imaging, and placental localization, you can use the chromium-51. Okay? Except for this one, which you use to sterilize your medical equipment, you could see all of them are what? Short term. They have a short half-life. Right? What's my, what we call person experience here? The iodine 125. It's my wife. So he had problems with her thyroid. Okay. This is something to do with goiter. So he was given what we call an iodine 131. So for 8 days, she had to isolate herself. Okay. Until the iodine 131 that was given to her concentration go down. Okay, so that's what we call one good applications of this nuclear isotope. So in the medicine, this is where they are usually used if you want to have this what we call bone scan. And I also have what we call experience in using these radioactive materials. Are you familiar with the Krebs cycle? Anyone?
Yeah.
Okay. So how do you think they were able to monitor the progress that they have there? So what they do, they have this what we call radioactive labeled, or the so-called radio labeled element. So if I'm not mistaken, it's a C6 material that they have there in the radiocarbon. So what they do is they labeled, I'm not sure if it's the tritium or the carbon 14. So what they're trying to do is in every step of the process, they try to monitor what is happening to that isotope. Okay? Because we also try to label it when I what we call the did some graduate study. So I have a tritium labeled tetracycline. It's an antibiotics. So what I do is I try to apply it to the plant. And then when it grow up, I try to monitor what happened. What's the form of my antibiotics that was put there. And then the next thing that I did is I use it to my SHIT sample. Why did I call it like that? Because it involves poop, wastewater. Sorry for those who are eating. Okay. So poultry manure, cow dung. Because what I'm trying to do is I want to see what happened if this is mixed to that material. Because I want to see what's the use of these antibiotics as growth promoter, what will be its effect. Okay. Because I don't know if you are the type of person that is fond of the so-called what? Organic stuff or organic food. Maybe you will hate me for what I will say, but those things are just this. What does organic food being fed of? Fertilizers from what? Anyone? If you have organic food, that means you never apply pesticide, you never apply fertilizer out of it, right? Commercial pesticide or commercial fertilizer. So how do you think the organic food is provided by its fertilizer? So usually you put animal waste. But what if I tell you that based on the study that I conducted, most of the antibiotics given to the animals, okay, they don't absorb it. 80% of them are what? They came out as waste. So if you're going to apply the waste that contains those antibiotic materials as fertilizers on your organic food, you are introducing those antibiotics in the organic food. That's why this organic food, they just make your pocket heavier. They're more expensive, but they don't give the nutrients that they said they will. They may give you the nutrients, but they will also include some materials that came out from the animal waste that they applied as fertilizer. Okay, so that's the finding that I have, and that's the basis of my dissertation. Okay, so how do you do this detection of the radioactivity? So you have this Geiger counter. I have used that thing. Okay, because if we use radioactive materials, every week we are being inspected for the use of our radioactive stuff. We also have that capability here at Pace University. So it just gives you some sort of a sound if there's some what we call the radioactive materials around. So if you're going to look at the biological effects of radiation, so they have this so-called RAD, radiation absorbed dose. So 1 rad is equals to 1 times 10 to the negative 5 joules per gram of material. Or they call it the REM, not the band. Okay, so the Röntgen equivalent for men So 1 rem is equals to 1 rad times Q, which is the quality factor. And the quality factors are this one, gamma, beta, and alpha. So if you're going to look at the average yearly radiation dosage for people like us here in the US, so this is what we have. So you have cosmic rays, 20 to 50%, ground and surroundings, 25%, human body, 26%. Look at this one. If you have X-rays, most likely you're exposed. Okay. If you do air travel, you're exposed. Fallout from weapon tests, you're exposed. Nuclear waste, you're exposed. So total between 133 to 188 REM. Okay. Now, there are a lot of applications aside from what we have discussed in the medicine and in the science. Another experience that I have also when I was in the Philippines. So I don't know if you're familiar with this one, right? Or maybe if you're not familiar, I have one here. Just wait. This one, right? So one island that we have here, one island province there, is very popular as producers of mango. So a friend of mine was a researcher in the nuclear research institutes in the country, asked me, what can we do about this problem in the insect pest? It's some kind of a pest. And then we said, we read in the literature that if you expose the pest in radioactive, make it radioactive, they become sterile. And there's a chance where their mate, okay, the species that they make will also become sterile. So in 1 year, we're able to solve the problem of the insect infestation because we're able to eradicate the insect population. Maybe it's what, genocide on the insect, but it's to save the mango industry in our country. So what we did is we just sterilized by radioactivity some of these insects and then put them in the area. I think that's what they done with dengue in Florida. Okay, but I'm not sure if they use radioactivity. I think they use GMO mosquito to eradicate the one that has the dengue. Okay, so that's just what we call what nuclear thing can do. Okay, and the thing, I don't know if you knew it, is it can also be used for food. Okay, so low dose inhibits sprouting of potatoes, onions, and garlics, and activate trichinae in pork. Medium dose, it delays the spoilage of meat and poultry. High dose, sterilize meat and kills microorganisms. But this is the thing that we have observed, because I have a paper about a herbal plant that the higher dose that it has, the more it affects the quality of the material. Okay, so just to see how good this food irradiation, so this is a non-irradiated, so this is the natural one. So this is the one that was irradiated at a lower dose. Okay, so the use of radiation, or the term that they have there is food irradiation, the process of exposing food to ionizing radiation to kill microorganisms, bacteria, viruses, or insects that might be present in the food, giving the food a long shelf life. So irradiation kills harmful bacteria to make your food safer. So they usually use cobalt-60 or cesium-137. So if you have an irradiated meat, it can have 3 months without refrigeration. See how good it is? And I can assure you, you're not going to become like an X-Men when you are what we call eating this low dosage irradiation. Okay, so dates to remember. So you have a practice exam on April 20. You have your what we call third exam on April 22. And the April 29, you have the final exam and whatever's the deadline on the out. And the final exam will cover everything. Okay, so question?
So does that mean the extra credit chapter 20 hour will be due
On the 29.
Okay, great.
I'm trying to get something here if I can share it with you. Because I know I usually share it every year. That, you know, James Bond's first movie until the last movie has something to do with nuclear chemistry. I'm not sure if I have the video right now. But since we still have enough time, I can always get my, what's that? I hope I can find it. Ah! I'm just trying to show this to you. 20. I'm trying to find that. Bun. Where is it? Periodic table, thermal. Oh, yeah. I'll try to see.
Cyanide in a cigarette? Fantastic.
Hydrogen cyanide?
Those samples Strangways brought back from Crab Key were radioactive. Yet Professor Dent told me they were worthless chunks of iron ore.
Oh, it's a depleted uranium shell, military grade. Hard to get, extremely expensive, and only used by a select few.
Okay. So that's just one. But the last one that I have there, okay. What's the latest James Bond? Before the one that should be open this year. There's
Spectre.
the Spectre. So there's a scene there about thallium. Well, the one where when one of the former villain was poisoned by thallium. I just cannot find the thing on that what we call scene. I'll try once again, try to search about it. So why I'm searching for it, so what's my thing, because we're not done with the slide yet. So these are the things that you need to remember for the coming weeks. So that what will you do in your 2 weeks, so that by May 1, okay, you can start deneuralizing yourself. Because most of the time, after you're done with the course, you also forget everything about the course. Okay. So just do that maybe by May 1st. And you will be okay with your what we call course. So please type now what you wish for. So you will never know what's the top list there, and maybe we can be it can be provided to you. Because what will happen, I will have a change in grading right now. I'm going to coordinate with Dr. Maisis the grading because her style is to add points. My style, which my former class don't know, is to reduce what? To reduce the grade. I don't know if you know it, but once you grade a total score of 90, that's an automatic A. Although in paper, the A should be what? 93. Okay. So I like to just meet with her when we do the what we call the final grading, so that there will be what we call some sort of standard in the grading that we have. Okay. So the way that you can always earn the thing is you work for it. That's always been my what we call the policy. Okay. So usually if you work for it, you will get it. But if you don't work for it, then that's it. Okay. Everyone should know that the world was not made for you. Okay. Sometimes you have to work for yourself to get what you want. Okay. So I'm going to turn off the thing. So every wishes that you might have might not be included in the record thing. I cannot find the thallium thing. So questions so far?